So, good afternoon. I will wait for 2 more minutes for others to join, then I will start. Okay, let's start. So, good afternoon. Welcome to the week 10 problem solving session for week 10 for the course Environmental Chemistry. So, let's start. Let me first share my screen. Okay, the week 10 was about two topics. The precipitation of solids. There was two lectures for precipitation of solid. One was for precipitation and next was for if there are more than one solid precipitating, that is for competitive solids. Then the next three lectures was about redox reactions. So now introduction about redox reaction, what are its applications, where it is applicable in real scenario where we see redox reactions, and also how to balance a redox reaction followed by its kinetics. All these were covered in the week 10 materials. So the assignment will be also a mix of this, like there will be questions on precipitation of solids also, and there will be questions on balancing of redox reaction. There will be question on the balancing, finding the oxidation state of the compounds, etc. So let's start. So this course is instructed by Professor Bhanu Prakash Velanki from Department of Civil Engineering, IIT Roorkee, and I am one of the TA for this course. I am a PhD scholar in Civil Engineering Department at IIT Kanpur. So I think we should directly go to the assignment part. So let's see what is the first question. So the first question is we have to match the following. So four things are given: oxidation, reductant, reduction, and oxidant. So we have to match these 4 points with the corresponding correct explanation or definition for this. Okay, since there are no participants, I will directly go to the solution. So first is oxidation. So oxidation is the process of donating the electron. It was also very well, it was also there in the lecture slides. What is oxidation, what is reduction, what is an oxidant, and what is a reductant. So oxidation is the process in which a compound donates its electron and its oxidation state increases. So for A, Q is the correct option. Okay, let's move to reductant. Whereas reductant and oxidant, these are the two compounds. Suppose if it is a reductant, then it will itself get oxidized, but it will help in reduction of something else. Something else, that is, if we are adding some reductant, then it will get oxidized itself and it will reduce the other compound present in the system. So reductant is something that that reduce the other compound. So for B, S is the correct option. Okay, let's move on to reduction. Again, reduction is the process where a compound accepts an electron and itself get reduced. So for reduction, R is the correct option. So for C, R is the correct option, that is accepting the electrons, and last is oxidant. Like reductant, oxidant is also a compound which itself get which itself get reduced but oxidizes the other compound. So for D, oxidant is something that oxidizes the other compound. So for D, P is the correct option. So based on this, we can say that B is the correct option. So oxidation is something in which it donates an electron. It is a process in which a compound donates an electron. Reductant is it is a compound which reduces the other compound. Reduction is the process of accepting the electron by a compound, and oxidant is something that oxidizes the other compound. So option B is the correct option. So let me tick it. Okay, I will directly write the answer. So answer is B. Also, if there is oxidation taking place in a system, then obviously there will be reduction also taking place in the system, because oxidation and reduction, these are coupled reactions, and overall reaction is known as redox. So a single oxidation and a single reduction reaction cannot exist, they exist in couple. So let's move to the next question. So the second question is, in the module video lecture number 47, when the instructor talks about the removal of arsenic present in the water using the redox process, why it is preferred to convert arsenous form to arsenate form. That is, arsenous is the arsenic 3 form, AS3 form, which is H3ASO3. Arsenous 3 form to convert to arsenate 6 form. Arsenate 6 is H3AsO4. Okay. So we have to find out which option is correct. Why it was told in the lectures, this lecture slide, that we have to convert arsenate 3, that is arsenic 3, to arsenate 6. So the first option is the removal involves redox coupling, preferring higher oxidation state compounds. Next is the removal is independent of the compound present and both form of arsenic are equally likely to be removed. And last is the arsenate form around pH of 7 exists in both H2AS4 minus and HAS4 2 minus, both enabling ion exchange for the removal. So these two compounds are, let me write it. It is H2AsO4 minus or HAsO4 2 minus. So we have to find out of these three which is the correct option. Okay, just give me a minute. Okay, first of all, this example was not in the lecture number 47, rather it was in lecture number 49. So sorry for this, there is a mistake, printing mistake in the question paper. So, so the correct answer is C, that the arsenate form around pH of 7 exists in both these two compounds, which enable ion exchange for further removal. So it was in the slides that H3ASO3 minus. So so this is an acid, so it will dissociate and it will exist as H2ASO3 minus plus H plus. Next again H2ASO3 minus, it will dissociate as HASO3 2 minus plus H plus and So sorry for taking so much time. So if we see the arsenous acid, so this is arsenite. So it will give 1H plus and form H2AsO3 minus, and its pKa value is 9.23. So till 9.23 it will exist as in the form of arsenite, that is H3AsO3, arsenite acid, and next pKa value is 12.1, and again the next pKa value is 13.4. But if we see the arsenate, that is H3AsO4, so it will dissociate at around pH 2.2 and form H2AsO4 minus, and at pH around 7 it will again dissociate and form HAsO4 2 minus, and at pH 11.53 it will form to and give arsenate ion. So if in some system we want to remove the arsenic by using ion exchange, then we need the compound to have some charge on it, because we are using ion exchange. So if we will use the arsenite, that is 3 form, then it will after pH 9.23, then after this pH maximum of arsenite will exist in anionic form. But generally the removal is with the pH of the water is in the range of 6.5 to around 8 or 8.5. So in that pH range it is better that we convert this arsenite form to the arsenate form. And because here we can see that around pH 7 the maximum majority exists as HAsO4 2 minus, and if we go slightly greater than that, then there will be also AsO4 3 minus. So that's why it is better to convert the arsenate to arsenite to arsenate form. Also, let's find out here only how to find out the oxidation state, that why it is AS3 and why it is AS6. Let's find out the oxidation state of these arsenic in these two compounds. So if we take the arsenite, that is H3AsO3. So we know that hydrogen has +1 oxidation state, oxygen generally has -2. So let's find out, let's consider arsenic has X. So overall it is a neutral compound. So overall sum of the oxidation state with the number of elements will be 0. So we have 3 H plus, so 3 into 1, plus we have 1 arsenic, so X into 1, and again we have 3 oxygen atoms, so 3 into -2, it will be overall 0. So on solving this, we will get 6 divided by, so it will be -6 plus 3, so it will be overall 6 minus 3, that is 3 plus 3, or 1, 2, 3. Next is, let's find out here only, H3AsO4. So again, let's figure it out. Let's assume it to be Y and -2. So 3 plus X plus 4 into -2 will be 0, and 8 minus 3 will be 5. So it is +5. So similarly, we can find out the oxidation state of any element in the compound. We will assume the element which we have to find out as X or Y or anything, and we generally know the oxidation state of hydrogen, oxygen, sodium, sulfur, potassium. So based on that, we can find out the oxidation state of the unknown element. So let's move to the next question. So here we have to find out the oxidation number only. So the compound given are, we have to find out the oxidation state of carbon in carbonate, chromium in HCrO4 minus, and antimony in this compound, and carbon in acetate ion. So I will give you 2 minutes for each. So please try to find out first for oxidation state of carbon in carbonate, then we'll move to the chromium. So just take your time and write your answer, whatever oxidation number you are getting in the chat box. Okay, let's see how to find out the oxidation number. So we will first see the carbonate ion, that is CO3 2 minus. So we know that the oxygen carries -2 charge and overall charge for this ion is compound is 2 minus. So let us assume the oxidation number of carbon as X. So it will be X plus, so 1 into X, so carbon, number of carbon in carbonate is 1, so 1 is number of element and X is its oxidation number plus number of oxygen atom is 3 into its oxidation number is -2 and the overall charge is -2. So on solving this, we will get that X is equal to -2 plus 6, that is +4. So carbonate oxidation state is +4. So it will be A. So similarly, we can find out the oxidation state of chromium. The compound given is HCrO4 minus. So we have to find out the oxidation state of chromium. We know that the oxidative charge on hydrogen is +1 and on oxygen is -2. So number of hydrogen atom 1 into +1 plus number of chromium atoms 1 into X plus number of oxygen atom is 4 into charge is -2 and overall charge of the ion is -1. So on solving this, that is -8 plus 1, that is -7. On going to the left hand side, it will be +6. So the charge of chromium in HCrO4 minus is +6. So +6 is for B. Let's move to the next compound, that is SbF6 minus. Okay, SbF6 1 minus. So we have to find out for antimony, that is Sp, F is fluorine, and we know that the charge on fluoride is -1. So let's assume it to be X. So number of atoms 1 into oxidation number X plus number of fluorine atoms 6 into charge on fluoride -1 and overall oxidation state, overall the charge on the compound is given as -1. So on solving this, we will get X as +5. So P is for C. And the last compound is, let me solve here. Carbon in acetate ion, that is C2H3O2 minus. So we have carbon, let us assume carbon to be X and let's proceed. So number of carbon atoms, it is 2, so 2 into X plus number of hydrogen atom 3 into charge, that is +1 plus number of oxygen atom 2 into charge -2 and the overall charge on the compound is -1. So on solving this, we will get I think we are getting 1. So it is -1. 2 to the 4, it will be +4 and -3. So it is +4 -4, it is 0. X is 0. So it shows that the average charge of carbon in acetate ion is 0, but it doesn't mean that C, we have we have two carbon atoms. So C, and it is attached to so we have CH3, 3H atoms. Let me write it here. C2, see this is carbon number 1, this is carbon number 2, and we have two oxygen ions. So this is, and this is the minus charge. So just now we have find out that the X is the average oxidation number of all the compound of all the carbon atoms in this, and it is coming out to be 0. But it doesn't mean that C here it is oxidation number will be 0, and C on C, let's name it as C1 and C2. So it doesn't mean that the oxidation number of C1 is 0 and C2 is also 0. So let's find out what will be the oxidation number. So since it is an organic compound, in organic compound we find out in any compound it is an organic compound. So organic compound can have number of carbon atoms. So we are finding out the average oxidation state. So let's find out the individual oxidation state of C1. So we know that carbon is more electronegative than hydrogen. So carbon will have negative charge and hydrogen will have positive charge. So there are three hydrogen, 1, 2 and 3. So there will be plus 1, minus 1, because hydrogen is hydrogen is less electronegative, it is more electropositive, so it will have plus 1 charges. And since hydrogen is plus 1 charges, so carbon will have minus charges. So 1, 2 and 3. So there are 3 hydrogen atoms, so it will be minus 3. And on the right hand side, we can see that carbon is bonded to carbon. So there will be no charge from this carbon to this, or there will be no traction or repulsion. So it will be 0. So here the overall oxidation state of carbon C1 is minus 3. Let's find out for carbon C2. So here we know that oxygen is more electronegative than carbon. So oxygen will have negative charges and carbon will have positive charge. So here it is attached with carbon. So it is minus 2. And there are two bonds. So it minus 1, minus 1, minus 2. And again minus 1 from here. And it is minus 3. So we can see that, sorry, it will not be minus, it will be plus, because oxygen is a more electronegative ion atom. So carbon will have positive charges, so it will plus 3 and it is minus 3. That's why the overall oxidation state is 0, but the oxidation number of C1 is minus 3 and C2 is plus 3. So let's move to the, similarly we can also do one more example for glucose. We can do it here. So glucose is C6H12O6. So let's first find out what is the oxidation number of carbon in glucose. So let's assume it to be X. So we have 6 carbon atoms, 6 into X, plus we have 12 hydrogen atoms, into charge we know is plus 1, plus we have 6 oxygen atom and charge on each will be minus 2. And overall is 0. So on solving this, we will get X. Let me solve that. 6 to the minus 12 plus 12. So we are getting the oxygen number, oxidation number as 0. And glucose is a type of sugar, so it has like a strong cyclic structure. So let me first see the structure of glucose. Okay. So this is the structure of glucose. Glucose also exists in cyclic forms. Let's not go into that. I think it form one. There is a cycling of the structure at I think 1 and 4 carbon atoms. I don't remember it properly. So let's not go into that. So this is the glucose, overall glucose molecule. So we have 1, 2, 3, 4, 5 and 6 carbon atom. So let's find out what is the oxidation number of each carbon atom. So if we see at carbon 1, that is C1, so H will have plus 1 charge and oxygen will have minus 2 charge. And from carbon to carbon, there will be no charge on the atom. So from here it will be 0. So that is charge here will be, from here it will be minus 1 and from here it will be plus 2. So plus 2 minus 1 it will be plus 1. And let's go to the carbon number 2. So from carbon it will be 0, from hydrogen it will be minus 1 and oxygen again it will be minus 1. So C2 has oxidation number of 0. Similarly C2 and C3 we can see the arrangement of atoms here is similar. Here again from oxygen it will be the plus 1 and hydrogen it will be minus 1 and from carbon 0, so oxidation state is 0. Similarly for C4 it is 0, from carbon it will be 0, hydrogen minus 1 and oxygen plus 1 is 0. Again for C5 if we see it is again 0, and if we will see for C6 then from carbon it will be 0 and it has 2 hydrogens, so minus 1 minus 2 and from oxygen it is plus 1, so minus 2 plus 1 it is minus 1. So we can see that each individual atom have different oxidation number and overall oxidation number is different. So since C1 has oxidation number of plus 1 and C6 has oxidation number of minus 1, so plus 1 and minus 1 and plus 0, 0, 0, it is 0. So overall average oxidation number of carbon in glucose is 0. So let's move to the next question. So the question is, determine the correct statements out of the following. First is, for monoatomic components, the oxidation state is usually 0. Next is, in a covalent compound, the oxidation state of each atom in the charge remaining on the atom when a shared pair of electrons is assigned to the more electronegative of the two sharing them. Next is, the covalent compound with two similar atoms bonded together has 0 oxidation state. I think the slides are not changing. So we have to find out the correct statement out of the four. Multiple options are correct, so that's why combination of options are given at the last. So we have to find out which of the following are correct. So I'll give you 2 minutes to just read the question and find out which is the correct option, and just write your answer in the chat box. Okay, let's see what are the correct options. So first is, for monoatomic components, the oxidation state is usually zero. First of all, most of the elements do not exist as monoatomic except the noble gases, that is argon, helium, xenon and all. So these exist as monoatomic and they have oxidation state of zero. But except these, all the compounds do not, they exist as monoatomic component, but their oxidation state is not zero. So if we take sodium, then it has Na plus charge. If you take chloride, that is Cl minus charge. And if you take calcium, it has Ca2 plus charge. So the first option is not correct. So for monoatomic components, the oxidation state is usually equal to the charge on that element. So for sodium, the oxidation state will be +1. So for chloride, it will be -1, and for calcium, it will be +2. Next is, in a covalent compound, the oxidation state of each atom is the charge remaining on that atom when a shared pair of electron is assigned to the more electronegative of the two sharing them. So this is also correct. So suppose if you take a covalent compound, let's take CH3OH, that is methanol. So let's split out. So in this compound, we can see the more electronegative atom is oxygen as compared to carbon. So the more electronegative atom will be the oxygen. But if we see in carbon and hydrogen, the more electronegative atom will be the carbon. So if there is sharing between sharing of electron between hydrogen and carbon, then electrons will be a little bit aligned towards carbon. That's why hydrogen will have plus charge and carbon will have minus charge. This is all written in the statement that the shared pair of electron is assigned to the more electronegative atom of the two sharing them. So for carbon and hydrogen bond, the shared pair of electron will be assigned to the more electronegative atom, that is carbon. But in case of carbon and oxygen, the shared pair of electron will be assigned to the oxygen. So here oxygen will have -1 from hydrogen and -1 from carbon. So here oxygen is having -2 oxidation state. Hydrogen is having +1 oxidation state. And carbon is having -1 from this hydrogen, -1 from this, and -1 from this. But for in between carbon and oxygen, the electron pairs will be assigned to oxygen, and carbon will have -1, -1 from 3 hydrogen atoms. And so let's add this. And it will have +1 from oxygen. So overall it will be -3 plus 1, that is -2. So this is written in the statement number B. Next is the covalent compound with two similar atoms bonded together has zero oxidation state. So this is correct. Suppose example is given. There are two chlorine atoms. So these two are the same atom, or these two are the same similar atoms. So the shared pair of electrons will be distributed between these two, and it has overall oxidation state of 0. Similarly, it is true for oxygen also. Oxygen atom, sorry, it has overall oxidation state of 0 because the shared pair of electrons are equally shared between these two atoms of the oxygen. Next is the sum of oxidation state for atoms in multi-atomic substances is 0 for molecules and equal to ions formal charge. So this is also correct. So if we suppose we take example of C6H12O6 glucose. So the sum of oxidation state will be 0. I should say state or number, it will be 0. But if we take carbonate, that is CO3 2 minus, then here the sum of oxidation state will not be 0, rather than it will be equal to the charge on the compound, that is -2. So this is written in the last statement. So option number B, C and D are correct. So this is the correct answer, that is D is the correct answer. Let's move to the next question. So we have to determine the reductant and oxidant in the following reaction. In the first question also itself, there was match the following question type, in which reductant, oxidant, reduction and oxidation was asked. So reductant is something which itself get oxidized but reduces the other compound, and oxidant is something which itself get reduced but oxidizes the other compound. So in this reaction, we have to find out the oxidant, or which one is the oxidant and which one is the reductant. That means which one is going under reduction and which one is going under oxidation. So I'll give you 3 minutes to solve this question. So just take your time and find out which is the oxidant and oxidant and write the correct option in the chat box. Okay, let's see what is the solution for this question. So we have to find out the reductant and oxidant in the following reaction. So the reaction is chlorine aqueous plus 2I, that is iodine. It is giving 2Cl minus plus I2 aqueous. So we have to find out of chlorine and iodine which is the oxidant and which is the reductant. So as I told you, oxidant is something which itself get reduced but oxidizes something else. That is, oxidant is getting reduced, so it will accept electrons. So let's find out what is the oxidation number of each of these the compounds in the reaction. So it is Cl2, two chlorine ions, sorry, two chlorine atoms bounded together. So the oxidation number here will be 0. Again, it is 2I minus, sorry, there is mistake, it is iodide ion. So here the charge is -1. Again here charge is -1 and for I2 aqueous it is 0. So we can see that chlorine is going from oxidation state 0 to -1. That is, it is accepting one electron. So since it is accepting one electron, so here reduction is happening. That is, chlorine is converted to 2Cl minus, so it is reduction. Since chlorine itself getting reduced, so it is an oxidizing agent. So it will be a oxidant. So Cl2 it is a oxidant. So we can if Cl2 is an oxidant, then it is obvious that I minus will be the reductant. But let's see what is happening here. So for I minus, it is converting to I2. Oxidation state is going from -1 to 0. That is, it is donating one electron. So if something is donating one electron, so this reaction is a oxidation reaction. And now since iodine is itself getting oxidized, so it will be a reductant. That is it is giving electrons, so something else will be accepting the electrons. So since it is giving electrons, so it is oxidizing, so it is a reductant. So I minus here is the reductant. So chlorine is the oxidant, so chlorine is the oxidant, and so option A is the correct option. So oxidant is something which itself get reduced but oxidizes the other compound, and reductant is something which itself, so I think I said wrong. So oxidant is something which itself get reduced but oxidizes something else, and reductant is something which itself get oxidizes but reduces the other compound. So let's move to the next question. Find out the number of H plus ions in the balanced half reaction of the following couple. So nitrate is converting to nitrate ion is converted to nitric acid, that is HNO2 plus. So we have to find out the number of H plus ions while balancing this half reaction. So first, okay, I'll give you 3 minutes to balance this equation and find out the number of H plus involved in this reaction. Okay, let's see how to solve this question. Let's find out whether it is a oxidation reaction or it is a reduction reaction. So nitrate, that is NO3, NO3 minus is forming HNO2 plus. So let's find out the oxidation number of nitrogen on each of the two compounds. So it is X plus 3 into minus 2, and overall it is minus 1. So here it is X is plus 5. And if you see here 1 plus X plus 2 into minus 2, it is plus 1. So X is so there the oxidation number of nitrogen is going from plus 5 to plus 4. So it means it is accepting one electron. Since it is accepting one electron, so it is a reduction reaction. So let's try to balance this equation. So nitrate is forming HNO2 plus. So generally what happens, we will balance everything except hydrogen and oxygen. So here it is nitrogen, and we can see that nitrogen atom is balanced because there is one nitrogen in the reductant side and one nitrogen in the product side. Next, what we are going to do, we will balance the oxygen. So here we can see that here it is 3 oxygen and here it is 2 oxygen. So we will balance oxygen by adding HO2, water molecule, that is H2O. So here it is 2 plus 1, 3 oxygen, and here it is 3 oxygen. So nitrogen is balanced, oxygen is balanced. Next, what we will balance is, we will see, next we will balance the number of H plus. So here it is 1 plus 2, that is 3. So we will balance 3H plus. So nitrogen is balanced, oxygen is balanced, and hydrogen is balanced. Next, finally, we will balance the charge on both the sides by adding electrons. So let's see, on the right hand side, that is in the product side, the overall charge is plus 1. But on the left hand side, we can see the charge is plus 3 minus 1, that is plus 2. So to balance the charge, if we will add one electron, that is, let's add one electron. So now we can see that the charge is plus 3 and minus 2, that is plus 1. So this reaction is balanced. So let me write the overall reaction. 3H plus 1 electron plus nitrate. It is forming HNO2 plus and H2O. So this is the overall balanced reaction, and we can see that 3H plus ions are needed to balance this half reaction, which is a reduction it is C half reaction. So the correct option is C. Let's move to the question number 7. So this question is based on precipitation of solid. We have to solve in Mintek. So let's see what is the question. Ferric chloride is often added as a flocculant to water in treatment plants. For the problem below, so it is a common data question for question number 7 and 8. For the problems below, the ferric chloride added is this much, and assume that Ferrihydride is the only solid that forms. Solve the following questions with V-Mintek. So the first question is determine the pH and dissolved ion concentration in percentage terms if ferrichloride were added to pure water. So we have to find out the pH and dissolved ion concentration in percentage terms. So let's see how to solve this question. Okay. Uh, so this is the Wiesel-Mintek interface. So what we have been given is that ferrichloride is added as a flocculant. Generally in what happens in water, the colloidal particles generally have negative charge. So we add some cationic coagulant so that the charge of the colloids is neutralized and colloids gets destabilized, and finally they settle by formation of the flocs. So let's try to solve this question. We have to find out the pH, and it is given that FeCl3 is added is 10 raised to the minus 4 moles. Uh, so let's add FeCl3 will dissociate in Fe3 plus 3 chloride ions. So first add Fe3 plus, it is given as 10 raised to minus 4, that is 1e minus 4. Unit is molar only, so we will add it to the list. Next we will add the chloride ion. It will be 3 times, so 3. We will add it also to the list. We have to find out the pH from mass balance. Ionic strength will be calculated, and it was given that ferrihydride is forming. So let's add the infinite solid phase. Let's limit it to the species which we have added. So we have to add ferrihydride. We will add it to the list. We can see from list of fixed species, yes, ferrihydride has been added. Now let's run the Mintek. So we can get, we'll see that the pH is 3.537, and there was one more question that we have to find out Fe3 plus dissolve in percentage. So we will go to the equilibrated mass distribution, and we can see that I think I have done some mistake. Okay, actually I was seeing the equilibrated mass distribution, but we have to see the species distribution. So in the species distribution, we can see that around 2.05 percentage of the total concentration is Fe3 plus. So let's go back. So the pH was 3.5. So let me write it down here. pH was 3.5. 3, 7 or 6, I guess. And from the species distribution, we see that Fe3 plus dissolve was 2 point. Two point 0.05%. So the correct option is D. So I'm writing with the cursor, so I'm sorry for the handwriting. So we have find out the pH and dissolved ion concentration. pH is 3.54 and Fe3 plus dissolve is 2.05%. So correct option is D. Let's move to the question number 8. So these are the screenshots from the Vimentech. So question 8 is, if water initially had alkalinity of 150 milligrams per liter as CuCO3 and pH of 8.3, assume that the alkalinity is from dissolved or inorganic carbon. What are the pH and dissolved ion concentration at equilibrium? So in question number 7, we have assumed that we are adding FeCl3 in pure water. It is in the statement here that we are adding FeCl3 were added to pure water. But in question number 8, it is given that we are adding FeCl3 in water having some alkalinity and pH was also given, and we have to find out what will be the pH after adding FeCl3 and what will be the concentration of Fe3 plus dissolved. So let's solve this question using Vimentech. So let's go to Visual Mintech. So since in this question alkalinity is given, so what is the approach that we will specify the given alkalinity as CaCl3 in the Vimentech. We will also fix the pH as at 8.3, and after running the Mintech, we will find out what is the total concentration of calcium and total concentration of carbonate. We will note down the concentration of calcium and carbonate, and again we will reset everything in the Vmintech, and we will add calcium and carbonate as species in the list of species added along with ferric chloride, that is Fe3 plus and Cl minus, and we will again run the Mintech and we will see what is the pH and distribution of the species. So let's go to the Vmintech. So let's first reset everything. So in question number 8, let's add first the alkalinity. It is given as 150 milligrams per liter as CaCO3. So we will add it, and pH is fixed at 8.3. Sorry. Now we will see whether we have added. Yes, we have added the calcium carbonate. So we will run Mintake. So this is the overall distribution of the species. So we can see from here, this is the distribution of carbonate. Now what we have to do is, we have to go to equilibrated mass balance, and we will see what is the concentration of carbonate and what is the concentration of H plus. So this is the overall concentration. So we will note down what is the carbonate and H plus concentration, and again we will run the Mintake from very start. So let's go back to input menu. We will reset everything, and we will add the concentration of H plus and carbonate which we have get just now by specifying the alkalinity and fixing the pH at 8.3. So carbonate was, okay, let's find H plus was 2.9941 E minus 3. Let's add to the list. And carbonate was 2.9959. So 2.9959. We will add to the list. We can also cross check whether we are getting pH 8.5 by running the Mintake. So we can see that we are getting pH 8.5 only. So let's go back, and in this system we are adding 10 raised to minus 4 molar of ferric chloride. So let's add Fe3 plus, that is 10 raised to minus 4 1 E minus 4, and let's add chloride. Chloride will be 3 times of the ferric concentration, so 3E minus 4. So we can cross check by going to view or edit list. We have added ferric and chloride. So let's go back. So let's run the Mintake. I think we have to specify the solid also, it was given. Let me see the question. So in the question it is mentioned that ferrihydride is the only solid that's formed. So let's add the solid. So we will specify the infinite solid phase. We will add ferrihydride. Okay. Now let's run the Mintake. So the pH is 7.284, and we have to find out the Fe3 plus percentage, and we can see that Fe3 plus is not here in the species list. It means the percentage of Fe3 plus at this pH is 0. So let's go back and see which one is the correct option. So I hope this question is clear. Alkalinity was mentioned along with the pH. So we have fixed the pH, we have added the alkalinity, and we have find out how much H plus, what is the total concentration of hydrogen, H plus, and total concentration of carbonate. Again, what we have done, we have input the value of carbonate and H plus along with ferric chloride, that is Fe3 plus and Cl minus, and also we have added the solid which was specified in the question, that is ferrihydride, and we have run the Mintake. After running the Mintake, we are getting the pH of 7.284, and if we will go to the species distribution tab, we will see that Fe3 plus is very less. Sorry, Fe3 plus is not in the species name. So its concentration is 0 at given pH. So let's go back to the question. So the pH is 7.3 and Fe3 plus dissolve is 0. So the correct option is option A. So A is the correct option. So let's move to the next question. So these are the next question number 9 and 10 are connected questions. So I think this question is based on redox. So the question is, the presence of iron in natural waters has been known to create problems in potable water treatment and distribution system. The removal of iron is essential to make water aesthetically acceptable and ensure the integrity of the distribution system. Conventionally, water treatment plants use chlorination and aeration to remove iron in water. It is proposed to use a strong oxidizing agent like potassium permanganate. Following is the proposed reaction. Reaction takes place when we add potassium permanganate to water. That is, Fe2 plus is getting oxidized to Fe3 plus. This reaction needs to be balanced by using the method of half reaction. What would be the number of H plus ions to be in half reaction of Fe2 plus, Fe3 plus couple and MnO4 minus and Mn plus respectively? So the question is given, we have to find out the number of H plus involved in the oxidation half cell and in the reduction half cell. So what happens in treatment plant, if some water has iron, then there is chances that iron oxidizing bacteria may develop in that water, and if we see that if some water has some iron and if we suddenly open the tap after in the morning, if the tap is not running for the whole night and if we open the tap, then sometimes it's like there is some fishy smell coming from the water, and that is due to the oxidation of the iron present in the water by the bacteria. This can be one of the reason. So generally it is tackled out by using chlorination or aeration, but we know that chlorination gives some form of carcinogenic compounds after chlorination. So generally it is getting omitted slowly. So let's go back to the question. We have to balance this reaction and find out the number of H plus involved in the oxidation half cell and reduction half cell. So let me go back. Find out. So we have Fe2 plus MnO4 forming Fe3 plus and Mn2 plus. So here in the question it is giving that we are oxidizing iron. Also we can see from the oxidation state it is going from +2 to +3. So this one is the oxidation. Again for manganese, let's find out what is the oxidation state. It is +2 and here it will be -8. It is +8, not -8. So from +8 oxidation state, it is going to +2. That means it is accepting 6 electron. So this is the reduction reaction. So this one is the reduction and this one is the oxidation reaction. Let's separately balance these two reactions. So Fe, let's balance the oxidation half cell. Fe2 plus is oxidizing to Fe3 plus. So first we will balance everything except oxygen and hydrogen. There is no oxygen and hydrogen. There is only Fe, and Fe is already balanced. Next we used to balance oxygen and hydrogen, but it is not required here. Here next what we will balance is number of electrons. That is charge on each side. So here it is plus 3 and here it is plus 2. So if we add 1 electron, the overall charge on the product side will be also plus 2. So this reaction is balanced. It is pretty much straightforward. Let's go back to reduction half reaction. In this MnO4, okay, it was MnO4 minus. So let me go back. So it is MnO4 minus. So the charge will be plus 7. So MnO4 minus is forming Mn2 plus. So we will balance the number of manganese. It is 1 here and 1 here. It is balanced. Next we will balance the number of oxygen. Here it is 4 oxygen. So we will add 4 H2O. That is 4 H2O. Next, after oxygen, we will balance the number of hydrogen. That is H plus. It is here 4 to the 8 hydrogen, but on the left side we will have to add 8 H plus. Next, at the end, we will balance the we will balance the charge on the reactant and product side. On the product side, the charge is plus 2, but on the reactant side, the charge is plus 7. So to balance it to plus 2, we will add 5 electrons. So minus 5, it will be again plus 2. So this is the reduction half reaction. So we have to find out the number of H plus involved in the reduction half cell and the oxidation half cell. So here H plus is 0 and here H plus is 8. So let's see which one is the correct option. So B is the correct option, 0 and 8. Let's move to the next question. So here in the question is the question was common data question for question number 9 and 10. The question number 10 is, in the finally balanced equation, how many moles of MnO4 minus would be required to oxidize 1 mole of Fe2 plus? So we have to find out the number of moles of MnO4 minus required to oxidize 1 mole of Fe2 plus. So let's see what was the oxidation half reaction and the reduction half reaction. So it was Fe2 plus So this was the oxidation half reaction and the reduction half reaction, and we have to find out first the overall reaction. So to find out the overall reaction, we can see that we will balance the number of electrons on the oxidation half reaction on the reduction half reaction. So we can see that in the oxidation half reaction, there is 1 electron is given by Fe2 plus, but in reduction half reaction, 5 electrons are taken by the MnO, each mole of MnO4 minus. So to balance this, we will multiply it by 5 and we will add. So equation number 1, we will multiply it by 5 and we will add it to equation number 2. So if we will multiply by 5, then 5 electrons here and 5 electrons here, it will be cancelled out. These and these two will cancel out, and what we will be left is, we will have 5 Fe2 plus plus MnO4 minus plus 8H plus. It will give us 5 Fe3 plus plus Mn2 plus 4H2O. So this is the overall balanced redox reaction for the given system. Like we were oxidizing iron Fe2 plus to Fe3 plus by using MnO4 minus. Potassium permanganate. But we have only taken the permanganate. So we have to find out how many moles of MnO4 minus would be required to oxidize 1 mole of Fe2 plus. So from here we can see that we are requiring 1 mole of MnO4 minus for 5 moles of Fe2 plus. So 5 moles of Fe2 plus requires 1 mole of MnO4 minus. So 1 mole of Fe2 plus will require 1 by 5 into 1, that is 0.2 mole of MnO4 minus. So we can find out by unitary method, which we have learned in, I think, class 7 or 8, that if 5 moles of iron require 1 mole of MnO4 minus, so we can find out for 1 mole. So 1 mole of Fe2 minus Fe2 plus will require 1 by 5 into 1, that is 0.2 moles of MnO4 minus. So the correct option is A. So these were the questions for the week 10 lectures. So I hope these questions are clear to you. Week 10 was a mixture about, the questions were about redox reaction and also about the competitive precipitation. So we have completed 10 weeks. Next, this is our 12-week course. So we are left with 2 more problem solving session based on week 11 and week 12 course material. And then I think there will be one more session based on the overall syllabus of this course, like what we have read, and and that will be the end of this course. And finally we will, I think we have the exam on 15th or 27th, I don't remember, but we have the written exam in the October only, and that will be all for this course. So thank you so much for joining. Have a nice day. We will meet next Sunday from 3 to 5 p.m. for problem solving session for the week 11 materials. So thank you so much for joining. Have a nice day.